Okay, it seems we are live now, so welcome. Welcome to the next Tuesday seminars here at the Warsaw University Astronomical Observatory. Today we have a speaker from Vilnius University, Edita Stonkute, sorry, she studied in Vilnius and she then did her postdoc in a couple of places around the globe, mostly in Lund. She visited Cambridge, for example, and Edita is involved in Gaia ESO project, some of you know about, and is going to tell us about high-resolution spectroscopic follow-up of planets and star-planet connection. Edita, floor is yours, please.
Thank you, Lucas. Good day, everyone, and thank you for this invitation. I'm sorry I can't be in person today with you, but I will try to give my message on the things that we do here in Vilnius, Lithuania. And today I'm gonna talk on actually high-resolution spectroscopic follow-up of planet hosts and candidates, planet host candidates. And then later on, I will present results on our last paper that we did together with the group that I am part of here in Vilnius University in the Institute of Theoretical Physics and Astronomy. And this work being done together with the main group had Gražina Tautvišienė. Probably some of you know Gražina very well. And then Šarūnas Mykolaitis, that he's also involved in Gaia ESO survey. And Renata Minkevičiūtė and Arnas Drasdauskas. So they are core people that did this work together with me. And before starting to speak about exoplanet hosts, I would like to remind you that basically in 1992, two scientists find a planet, and actually there were more than one planet, orbiting kind of not the one we expected star, but a neutron star. And this field started to grow up because few years later, we all know that Major and Qualos find a planet, actually hot Jupiter, around Sun-like star. And this discovery opened a new way to look at planets and how they form, and brought us a lot of surprises because it was hot Jupiter, very close to its host star. And this nice discovery has been awarded with the Nobel Prize a few years ago from now. And today, according to NASA exoplanet database, we have almost more than 5,000 planets around stars. And many more actually are waiting for confirmation. And this field of stars around other planets, the so-called exoplanets, grows so much, and thanks to extensive advances across observational efforts, and I'm talking about radial velocities method to detect planets, or transit, direct imaging, and even microlensing surveys. And with those surveys, we are able to not only detect exoplanets, planets around other stars, but also characterize them. And now we are going to the era when not only we are detecting planets, but also from high resolution and high precision spectroscopy, we can analyze the atmosphere from both ground-based and space-based observatories. And this is nice time to look at this field and to figure out what we can learn more by studying stars that host those planets. And combining overall information from observational side to theoretical data, we can try to figure out how actually planets formed, how they evolve, and to figure out their interiors and atmospheric processes. So I think it's a great era in this research field where we can all together, people who do spectroscopy of stars or do other observational things of stars, come together with people who do analyze exoplanets itself, and also trying to collaborate with scientists who do models, theoretical works. So it's a nice way to collaborate and engage. So if we look at these nice figures that I also took from NASA page, we see that the field started with radial velocity detection of exoplanets, and then the transit method took over, and we have many more planets detected using a transit method. And each year this number goes rapidly and increasingly. So if we look at what kind of planets we find, and I show you mass period distribution, you can see that planets that have been found with different methods clumps to three big groups, where we can call them hot Jupiters being very close to their parent stars, or normal classical giants that are more far away. And we can also see smaller planets like super Earth, and we can also see some rocky dwarfs or warm Neptunes. So we see also here the sensitivity, what kind of planets being discovered using different methods. And we can also see the nice imaging surveys are detecting those massive giants far away from their parent stars. And so this nice figure shows us that the planets that we find around other stars actually are a little bit different that we have in our own solar system. So one might start to think how you can form such diversity of planets. But my talk today is not on the planets itself, but trying to figure out what we can learn observing stars that host those planets. And we know that the composition of the star and planet actually are linked, because the first order approximation is that stars and planets are formed at roughly the same time and from the same original dust and gas cloud. And there are two methods how one can form planets, and the main method that not main, but the most attractive probably one is core accretion, where initial core forms two hierarchical sticking of smaller dust particles to smaller clumps to bigger planetesimals. And when the core is heavy enough, and the gas, hydrogen and helium also are created, and this is how giant planets can form. But the core has to have a sufficient core mass. And another method how we can form giant planets is gravitational instability or disk instability method, where there is a direct collapse from a gas cloud, and those clumps comes together, and rocky core actually is formed simultaneously by dust grains sinking to the center, and that's how we can form those planets. But whatever the planets were formed due those two methods, the composition of a star and planet are linked. So this is the idea how we can study star, indirectly study star. We can trace chemical composition of a star, know stellar parameters, and learn a little bit about planets. For sure, the missions that or telescopes that analyze atmospheres of planets will also be a benefit to this exoplanet research. So this nice ESO exoplanet research timeline shows that field started from ground-based observations when the first exoplanets being detected, to missions dedicated to find planets around other stars like Korot, Kepler, and then K2 mission boosted the number of known exoplanets, and many results, as you remember, came from this nice survey. And now TESS space mission will all sky mission using a transit method will find, and already several hundred planets are confirmed in TESS due to TESS mission. And the future missions like Cheops, Plato, Ariel will be also dedicated for exoplanet research. So in 10 years from now, we will have many more exoplanets that I'm showing you today, and probably we will open a new era of study with those nice detection missions. But also we need to remember that there are other space missions also sensitive to exoplanets like Hubble, Spitzer, Gaia, and James Webb Space Telescope, which will analyze atmospheres of exoplanets. So today, as I mentioned at the beginning of this talk, I'm gonna focus on the spectroscopic follow-up of planet hosts, of stars that host planets, and what I can learn analyzing stars and what we can learn about their planets and their diversity. So I would like to remind you that there is a connection between metallicity and giant planet occurrence rate. It was shown by work of Santos in 2001, where they analyzed FGK spectral type stars with giant planets and derived their metallicity in consistent way with a comparison sample that hosts no planet. And we can see the distribution of metallicity, iron over hydrogen, is skewed to the right, where we see that planets favor more metal-rich star. Later on, few years later after Santos, a big catalog of FGK type stars showed the same results, that the stars with planets percentage increase with metallicity. And now I'm talking about a giant planets. And metallicity actually plays an important role in giant planet formation. And naturally then arise another question, right? How about other type of planets? How about smaller ones? Can be less massive ones? can we also find any correlation with stars' metallicity? And in 2008, SAOSA analyzed the 66 planet hosts, and the majority of them at that time were Jupiters. And he also found few stars that host Neptune-sized planets. And he concluded that Neptune-sized planets Neptune-like planets do not form preferentially around metal-rich stars, because he also find a star with metallicity minus 0.4 dex. So this nice way forward to figure out how about other planets got attention, and GESIT in 2010 showed confirmation of SAOSA results at that time, that in his sample he has more Neptune mass planets. Number is still small in 2010, and he also said that Neptune mass planets do not form preferentially around metal-rich stars. And GESIT also nicely showed that if you add to your study more data from the literature, the distribution of metallicity, which is in red for Neptune mass planets, do not favor metal-rich stars as for giants. Okay, so naturally, when we had more exoplanets detected, there was a great debate to figure out how about rocky worlds, how about the smaller Earth-sized planets, or smaller ones than the Neptune. And a nice work, a nice follow-up of Stars with Planets led by Lars Buchave in 2014, they showed this nice planet radius and metallicity figure where they concluded that rocky planets can form at any metallicity, while we saw that ice giants preferably forms around metal-rich stars. Mini Neptunes also can form at any metallicity, because we can see the average, the red line is the average of the metallicity, but still with very high scatter as for rocky worlds. And this composition of the protoplanetary disk is thought to be linked to the composition of the host star, where higher overall metallicity provides building blocks to form a planet. And for rocky planets, the core accretion planet formation scenario is in favor, where higher metallicity implies more planetary building blocks. And we can see this nice studies here where they analyze this. So what else we can learn looking at stars with planets? We can also, that being done in 2009, Melendez saw that star, our sun, that hosts planets, shows a deficit in refractory elements with respect to solar analogs. And the abundance differences correlate strongly with condensation temperature, and refractory elements are with condensation temperature lower than 1000 Kelvin, and volatiles are less than this temperature. And Melendez at that time suggested that these refractory elements that sun is deficient comparing to solar twins, probably these elements are being trapped in terrestrial planets in our solar systems. This is why we see this nice turn by those refractory elements. And this work also got attention to figure out can we see if that is true taking bigger samples, or how we select stars. And actually, González Hernández in 2013 demonstrated that when we remove galactical chemical evolution effects, those differences disappear. So the red line here represents single stars that Hernandez analyzed, minus sun minus stars. We see this nice correlation. And after removing the chemical evolution effects, nor single stars nor planet host shows this trend with condensation temperature. And he said that it will disappear, the trend will disappear, and the volatile to refractory abundances ratios are very similar to solar values. So you can see that the field of exoplanet host really tries to figure out if that Melendez was suggesting in 2009, and Ramirez as well is showing the consistent results with different samples. And it's really the problem with Melendez's work was that the solar analog that Melendez took was only according to temperature. So he selected a comparison stars that are analogs to sun, just looking if they have similar temperature. But if you apply more restricted selection criteria, you will see that this disappear. And recently, Vardan Adyapian was looking at this planet and star connection in the way to figure out that especially for rocky exoplanets, how we can see this connection between stars and planets. And stellar abundances of major rocky forming elements like iron, magnesium, silicon are commonly used to infer the bulk composition of rocky planets, and especially in theoretical models. And the work that they did was they took all this rocky size super Earth planets from whole database. They selected small size planets, and they figure out the iron content of a star, of a host, and they associated this with a protoplanetary disk. And they also calculated, according to planets' mass and radius, and then density, iron content of rocky planets, and they found the correlation between star host iron content to correlation to planet rocky planet iron content. But what they are saying that this correlation is not, as we can see, is not equal to 1-to-1, and probably this is due to planet formation processes itself. So it's a nice work. I refer you to go and have a look if you haven't saw this nice paper. How about other elements? Are there any signatures that we try to look using different tracers? For example, lithium. What is the role of the abundances of other elements? And in 2009, Israelians showed that lithium abundances for exoplanet hosts that are here in red introduce additional lithium depletion, as we can see here, comparing to stars without planets. And this dashed line introduced the lower limit for the highest limit for lithium in stars with planets. because lithium abundances of solar type stars is expected to decrease progressively with age. And Israelis suggested that exoplanets might introduce amount of mixing and deepen the convection zone such that lithium can be burned. But later on, when the stars were selected also more carefully, this correlation, this planet host, later studies did not find these differences in stars with planets. For example, work by Bensby and Lind in 2018. So there are also other elements like alpha elements. In 2008, the Haywood and the Beckian demonstrated evidences of alpha elements enhanced in stars with planets. So the black running line is for stars with planets, and the green one is for comparison field stars. And we see at the metal poor regime, we have a high alpha for stars hosting Neptunian size and super Earth planets. And those terrestrial planets can be found in low iron regime, and they're mostly enhanced by alpha elements. And this early formation of rocky planets could start in galactic thick disk, where chemical conditions for formation of rocky planets are more favorable. How this works, say. And how about other elements? Can we also see any connection looking at other tracers? There have been a lot of different results in our field showing that probably stars with and without planets have no important differences if we look at this element versus iron and iron versus hydrogen trends. There are work by Delgado Mena when they looked at the refractory elements or high condensation temperature elements or volatile elements, that there is no difference between those studies. And as you can see in Suarez 2017 work, high mass planets are here shown in blue, low mass planets in green, and comparison sample in red, and they conclude that there is no differences if we look at the carbon abundance. But later on, Delgado Mena in 2021 showed that a low mass, lower than 30 solar masses, stars at lower metallicities actually are enhanced in carbon comparing to comparison sample or even to high mass planets. So it's interesting results. With more and more data, we can see some interesting patterns. So Delgado Mena sample with 122 and 634 stars for a comparison. So all this information that we can provide to the communities, I think is very important because theoretical studies show that carbon over oxygen number ratio, as well as magnesium over silicon, actually are important in determining mineralogy of planets. Because CO ratio controls the carbides and silicates formed in planets, where magnesium and silicon can tell us about silicate mineralogy, and there are works actually using CO and magnesium silicon abundances to tell more about mineralogy of planets. and also to constrain interior structure of rocky exoplanets. Stellar abundances such as I said, iron, silicon, and magnesium are actually key constraints to reduce the degeneracy in interior structure models and to constrain mantle composition, as it's been shown by Dorn 2015 work. Recent studies by Bitch and Battistini indicate actually large impact on planetary composition and planet formation pathways depending on the chemical composition of the host stars. And they are saying that CO ratio of giant planet host could help to distinguish whether if water ice condensation is the main driver in planet formation. And they are suggesting encouraging other future studies to incorporate not only metallicity as a key driver in planet formation, but also other abundances of different elements. So with this in mind, we started to build a spectroscopic follow-up, having a nice instrument at Moletai Observatory, Lithuania. This high-resolution spectrograph that we use here in Lithuania is with 1.65 meter telescope, and you can follow this QR code with your cell phones and go directly to our observatory webpage. The spectrograph that has three observing mode, three resolution modes, 30,000, 45, and 60, and the wavelength coverage is from 400 to 900 nanometers. So we build this high-resolution spectroscopic follow-up of known and possible exoplanet hosts. So we use the space, the test space mission conferred and candidate list to select stars to follow up, and we can observe till brightness 8.5 magnitude in northern hemisphere. We try to look for those stars. We try to observe those stars that has minimal, if any, chemical composition information, and from high resolution, I mean. And also there is a Europlanet Telescope Network that awarded us 7 with this VUES instrument, and we are continuous to observe stars with planets and derive all chemical composition as well as the main parameters of those planet hosts in homogeneous way. And so far we observed already more than 100 stars with planets. And today I will gonna present a little bit more about our telescope instrument and talk about this at the end, the last paper that we been accepted recently on the study that we done with this nice instrument and telescope, and this entitled Chemical Composition of Bright Stars in the Northern Hemisphere. Again, you can scan this QR code and go directly to the paper. The paper is with open access. So a little bit about the Moletai Astronomical Observatory. To the ones that do not know, it's in Lithuania. It's in very nice location in the middle of the woods. It's 70 kilometers from Vilnius. So we work in Vilnius in the Institute of Theoretical Physics and Astronomy, and the telescope that we work can be operated remotely, so we can observe at home or whatever we are at the moment of observation. Just a good internet connection is required. And we have three instruments. And one is this 35-51 centimeter Maksutov type telescope over here. Actually, there is no more trees around this telescope because it was disturbing to observe lower objects. And then there is a 165 meter Ritchie-Cartanian type telescope that we observe, we follow up planet hosts. And then there is a 33 centimeters Cassegrainian telescope that is in a year or so probably will be replaced with 80 centimeters telescope and new CCD cameras and detectors. So talking about instruments, I invite you to have a look. We have, as I mentioned, a shell spectrograph that we use for our study, and this, with this nice telescope that can be, as I mentioned, operated remotely, and then the CCD cameras, photometer, astrophotometer, radial velocity instrument, Coravel. So please have a look at the instrument if you are interested to learn more about them. And talking a little bit more about the high resolution VUES spectrograph, it was built recently by Yale University. So we have it operated since 2016. As I mentioned, it covers 400, almost 900 nanometers with 3 different resolution mode. And it has spectral rows from 70 to 153. And this is a shell spectrograph. And the working temperature is minus 94 Celsius. So with CCD detector. So we use this instrument for high resolution spectroscopy. And also, if you are interested to apply for observing time, we have a nice English application form. You just need to go there. They are in the web page. If you again scan it, you will learn that we have submission deadlines where you can easily apply and ask for a time with this nice instrument. And we have also transnational access in different projects. As I mentioned, Europlanet is financing if you want to observe with Moletai Observatory telescopes, and also Horizon project, chemical elements as a tracers of evolution in cosmos. So go there and learn if you are interested. And at the last minutes, I want to present the results that we done with this telescope and instrument. And as I mentioned, results are published, and we observed all bright stars in that are cooler than F5 spectral class in the area up to 12 degrees surrounding the northern TESS space mission continuous viewing zone, and this TESS continuous viewing zone, which is in red or purple, and it's also smaller ring here marks JWST place, and we extended this work to blue region, and overall, we have results for 740 slowly rotating stars, and uniformly we derived parameters like ages, orbital parameters, velocity components, and main atmospheric parameters and abundances for these elements that are listed here. So we have this big, nice catalog of uniformly derived data, and the ones who are interested more in how we did, what kind of techniques we used, I just want briefly to mention that to get the atmospheric parameters, we used equivalent width method of neutral and ionized iron lines to determine effective temperature, surface gravity, microturbulence velocity, and metallicity. I just listed temperature ranges and log G ranges and metallicity in order to understand what kind of stars we are looking at, FGK spectral type stars. And we use DAO-SPEC, a combination of DAO-SPEC and Moog to derive the parameters. And we we derived the parameters the same way that Vilnius node is deriving for Gaia ISO survey, And chemical composition or detailed abundances for 24 chemical species were derived applying a different method than the parameters. For the parameters, we use equivalent widths, and for the abundances, we use spectral synthesis method with turbospectrum code, and we use Mark's stellar atmosphere models where we took Gravies 2007 solar abundances, and we used the Gaia ISO line list for atomic lines. And here I show you a very important element like carbon, nitrogen, and oxygen that been derived using molecular bandwidths. And forbidden oxygen, we use a spectral synthesis method, and this elements requires to iterate. So first you derive oxygen and then carbon, and then go and check again oxygen, and then derive nitrogen. So it's quite of more time-consuming abundance determination than for the other elements. And also, if you look at how our results look comparing to other bigger spectroscopic surveys, so we found only 55 stars in common that being analyzed by Apogee infrared large-scale spectroscopic survey, and we see how our element minus Apogee for the same stars look like. This is the average of the different element, and we see that overall results are quite well taking into account that Apogee derives parameters and accordingly abundances from infrared spectra. And our results, we also try to look for the star-planet connection and look at the various chemical abundances and metallicity itself. And we have this nice plot where we showed thin-disk stars and thick-disk stars, and from 740 FGK spectral type stars, we only have in our sample so far 25 planet hosts. So our results on planet hosts only now are on those 25 planet hosts. So what we can see is that our element to iron ratio for alpha elements, where our alpha elements are magnesium, silicon, calcium, and titanium, both for high and low mass planets, where high mass planets are indicated in green and low in yellow, are systematically higher systematically higher than those for comparison stars at lower metallicities. If we look at this distribution, it's somehow still higher than overall comparison thin disk stars. Sure that the results are still sparse because of low number statistics. And if we look at magnesium over silicon, as I mentioned, very important number ratio, we see that there is we have similar magnesium over silicon ratio if we look to comparisons of stars and planet hosts. So we see no differences between those two samples. And how about CO ratio? And what we can see interesting here that if we look at high mass planets and low mass planets, the CO ratio increases with metallicity, and we see that low mass planets somehow has a higher CO ratio. The results are only for dwarf host. And we also looked at planet mass, but the planet mass can be divided our spectroscopic information from hosts and look at the planet mass. So we plot on the y-axis planet mass, and on x-axis various parameters like periods or stars, mean radial distance from galactic center, or height from the galactic plane, or metallicity. And here you see carbon, oxygen, CO ratio, magnesium, silicon, but now we have planet mass, right? So we have two groups of planets here that are, as we call in our work, low mass planets and high mass planets. And the gray points are results from latest mission work from 2021, and we also see some as in previous studies, that hosts that have high mass planets are more metal rich than the ones with low mass planets. And if we look at interesting tracers as CO ratio or magnesium silicon, and now we take only the dwarfs, because the purple ones are giants, and giants have different CO ratio because of the evolution of the stars, right? So we only take into account dwarfs. We can see that at the higher planetary masses, there is kind of correlation, a small one, but slightly more negative slope. And also, if we look at magnesium silicon ratio, we see this nice turn for higher mass planets. And we also looked at the condensation temperature, since we have in our sample a lot of comparison stars. So what we did for each star with confirmed planet, we find a analog star that has similar parameters. I mean, temperature, metallicity, belongs to the same population, either is thick or thick disk, similar age, and we try to look if there is any correlation with condensation temperature. And we divided this 25 planet hosts by 3 different colors, which means that green are for stars that host low mass planets, red for the stars that host low and high mass planets, and the blue ones are for the high mass planets host. And what we find here is that for the low mass planets, we find slightly positive correlation with condensation temperature. So here you can see that different elements have their own condensation temperature. So, and the star that hosts both type planets, high and low, shows even higher positive slope with condensation temperature. But if we look at hosts that has different kind of, not different kind, but high mass planets, as we call them in our sample, we see that those correlations are diverse, are either positive, either negative, either there is no correlations at all. So we also try to figure out if those what are the possible reasons for this condensation and abundance trend. And our results infer that we looked how the slope of element and how the slope that we've figured out in previous example correlates with metallicity of the host, temperature of the host, age of the host, and planet mass in Earth masses. And green represents thin star dwarf, orchid represents giants, and blue represents dwarf, the few stars dwarf. So we see kind of correlation with those parameters. So this work is just now done for 25 hosts, and with the follow-up that we are running now, we hope we can tell more about this topic and about those results. So with this, I would like, presenting our work, I would like to conclude that spectroscopic results from hosts actually provide important information for this exoplanet research field. And but is more important that small size telescopes can be used for spectroscopic follow-up of exoplanets, hosts, and candidates. And it's probably even easier to get time, to allocate time using those small size telescopes that are around Europe as well, not only in Moletai. And our overall results, the chemical composition, information on stellar ages, kinematic orbital parameters that we derived in our work for stars in Northern Hemisphere, I believe will provide useful priors for future exoplanet modeling as well as galactic evolution studies. And to finish my presentation, I would like to acknowledge the group that and the collaborators from Aarhus University that we did together. Hans Kelsen group and our Gražina Stotušinė group in Lithuania. So thank you for your attention.
Thank you very much. Thank you. Edita, questions to Edita? Here, Milena. If you could come forward to the camera here. If you stand here, you'll be visible. And
hello, thank you. I have a question about lithium. As you mentioned the depletion of lithium and its relation to planets. I wanted to ask about overabundance of lithium, because there were several cases where we linked overabundance of lithium and with the probably engulfment of planets, so actually that the planet existence before. Could you comment on that? Did you find that also in your results, some overabundance of lithium that could be a trace of previous planet existence?
Yeah, so regards engulfment of planets, we in our results, I think we do not have enough data to say if we didn't find overabundance. This work is by Israeli, right? And they have few planet hosts with more lithium abundance, but they said that those actually hosts have a higher temperature in their sample, so they associated with this with the higher temperature being responsible for the high lithium.
okay, thank you. Any more questions from here? Please come forward, Maya.
Hello, and
Hello.
thank you for Vanessa. And I have two questions. The first one is pretty basic, I think, and maybe you have mentioned that, but just to make sure, is it possible to say about the planet forming scenario just based on the metallicity of the host star? I mean, whether it was the disk instability or the correlation, or whichever this theory is favorized?
Yeah, I think that's a very good question, but only by looking at the metallicity, probably it's not enough to say which scenario can form the cell, right? So I'm not an expert in planet formation and modeling planet formation. So I believe they need more ingredients to learn if which scenario is more suited for a particular planet.
Okay, thank you. And the second question is more technical. So I know that spectra modeling and inferring is quite computationally expensive. So I wonder how much of computational resources did it take for your work? I mean, approximately how many hours or something like that?
Oh, it's a very good question, but it depends what you do, right? Per star, you mean, or?
It can be per star. I just wonder about the scale of computational expense here.
So it is very good question, and probably colleagues of mine are better to answer this. But per star, I don't know. It depends what you're doing. If you're calculating, you know, because we have several steps, like deriving atmospheric parameters. It can take several minutes to do for star. And to do abundances, it depends again what kind of chemical element you are looking at. As I mentioned, that to derive CNO abundances, it's more complicated if you want to look at your spectra, not only do it automatically, because there are difficulties to do those CNO elements. So it takes more human resources than computing power time. But for other elements, I don't want to lie to you. I can write you, but I don't know the number.
Okay, thank you.
It really depends how good the spectra is. If the signal to noise is, you know, for one star is better than the other, it really depends. It's not weeks for star for sure. It's hour per star or something like that. But it's, again, you need to, you know, it's iterative process. You check, yeah. And it's 1D calculation. It's not, you know, 3D and not, yeah, too much complicated.
And I assume that probably more than one spectrum per star. So
yes, exactly.
It multiplies, right? So
yeah, we have many different steps. Then we have raw data. Then there is a pipeline from the raw data that combines the flats and the scientific spectrum to create to create scientific spectrum. So we have different persons responsible for different tasks. One runs those pipelines to get the scientific spectrum, right? And then there are another person that runs the whole process to derive parameters. And then there are another person who do synthesis for many elements. And then there are a group who do CNO, because as I mentioned, CNO requires even to have a look at the spectrum, not only run it automatically.
Okay, thank you very much. I see there is a question from Marius.
Marius.
Okay. Hello, thanks to Edita for very nice presentation, and even more thanks to Warsaw University Tuesday seminars, because now I have opportunity to hear what my colleagues are doing. It's actually in the same office, but a few rooms away. But now it is the question. It is Edita, have you observed or have you got the spectra of any one star during the planetary transit?
Yeah, we had so with this big program that we run was together with Erika Pakštienė that analyzed the transit of planets. But as far as we did observe a star that has transiting planet, but Erika is still working on the results because she needed to have all from the beginning, then when the planet is starting to transit and ending the transit. So I don't know how good results are because we haven't been very lucky with the weather. But I hope that Erika Pakštienė will finally prepare those results and we will publish.
Okay, thank you. Very interesting. Okay, because yes, of course, if it is this transit planet, it is very rocky, like Mercury, like Mars. So probably we will see a simple, just little bit lower signal on the all wavelength. If it is this planet, it is with some kind of atmosphere, like Earth, like Venus. So probably we should expect some changes in the spectrum lines somewhere.
Yeah, but the problem is with observing those kind of Erika targets that usually they are very faint. So to get very good data with 1.65 meter telescope is pretty challenging because, as I mentioned in the beginning, we are observing up to 8.5 in V magnitude. And this spring we will illuminate our mirror, and hopefully we can get better signals even for 9-ish magnitude stars, because when it can.
Thank you.
Okay, thank you very much. Thank you for all the questions, and thank you, Edita, again for your talk. Thank you all for joining. Goodbye.
Thank you for invitation.